The geometry of closed superstring theory. I will be giving 3 lectures. The plan of first lecture is to tell you about the mathematical background needed for constructing superstring amplitudes, and then in lecture 2 I will describe the symplectic geometry of the moduli space of Riemann surfaces, and then in the final lecture I will try to explain you how to construct closed superstring field theory using all this mathematical background. So all of you are string theorists, but still I would like to say why I am doing string theory. So the main reason why I am doing string theory is that if you look into the spectrum, you can see gravitons, and if you compute the amplitudes, it's guaranteed that the amplitudes as a perturbative expansion don't have any ultraviolet divergence. That means I can consider string theory as a nice framework for describing the quantization of gravity. So that's my motivation for doing string theory. So I will be discussing superstring theory or superstring perturbation theory in the first 2 lectures. I won't say anything about the string field theory, because most of the techniques that is required for constructing string field theory is same as that that you need for constructing superstring amplitude. So let me start with string perturbation theory. Huh? Oh, okay, sure. Oh, this. We can do it. Yes,
Since they have visibility problem.
Okay, sure. Okay, sure. So there is no bound on the region that I can use.
They are able to see the whole mapping like
Okay, sure.
If it goes out of your line of view, please tell us. Yeah. Please don't run outside.
Okay, so the definition of string perturbation theory provides you a way to compute scattering amplitudes in string theory as an expansion in a coupling parameter. I will be discussing only about closed string theory. So the rules for computing amplitudes in string perturbation theory can be thought of as generalization of quantum mechanical rules that you use for studying point particles. So you can start from the quantum mechanics of point particles, the rules that you state using the path integral description, and then one has to just generalize to the quantum mechanical rules for studying an extended object. So we will be interested only in one-dimensional extended objects, and the quantum mechanical rule for point particle is that if you are interested in the propagation of a particle from position xa in space-time at time ta to xb tb, then what we are supposed to do is we are supposed to consider all possible world lines that connects these 2 endpoints. Then one can write down the amplitude or the probability for this process to happen as the square of an amplitude described in this scattering process or this propagation process, and take a square of it. Now how you compute the amplitude ABA? Here A corresponds to the initial state A and B represents the final state B, which is described by saying what is the position of particle in the space-time. So the path integral description of quantum mechanics provide you the rule for computing the amplitude. The rule is that you have to start with a weight factor or a phase factor I by h bar and multiply it with an action for each word line, and then sum over all possible word lines that connects A and B. So to get the or to study the quantum mechanical propagation of a string, what you are supposed to do is we are supposed to just generalize this prescription. So we have initial state A for closed string and a final state B for closed string. So we are supposed to consider all possible world sheets that can connect these two states. Now we have to give an action for each world sheet. So so that means the amplitude ABA for the string case is given by sum over all possible world sheets with initial state A and B, which I denote by MAB. So this is the prescription. So we have to understand what is, so understanding the phase factor is not that hard, but understanding the sum over all world sheet, that's the main thing that we are supposed to understand in string perturbation theory. So this is a simple case where you have a string propagating from initial state to final state B. So we can generalize this procedure for defining scattering amplitudes. So we can consider the interaction of n external string states and then study all possible world sheets that connects these 4 external states or n external states. So there are several possibilities. One is you have a world sheet that connects these 4 external states with a world sheet that has no handles in it, and then you can add handles. So you can keep on adding all possible number of handles. So you have an expansion that has infinite number of inequivalent terms, and within each term you have a sum over all possible world sheets that has this particular external state and a particular number of handles h. So this is the basic rule. Now we have to understand how to really perform this summation over all possible world sheets. So before that, let me tell you what is the action for each world sheet. So we have a world sheet that can be parameterized using coordinates sigma 1 and sigma 2. And then you have an embedding space-time coordinate x sigma 1, sigma 2. Then you can write down an action for each world sheet. So the action is the Polyakov action. The condition that action must have to satisfy are the following. It should be invariant under local Lorentz transformations that you perform in the space-time, and then it should be invariant under reparameterization of the world sheet coordinates. So such an action is given by the Polyakov action. That's given by 1 by 4 pi alpha prime, where alpha prime is the only parameter that you have in the theory. So this is a basic string scale. And then you have an action which is invariant under Lorentz transformations and the reparameterization on the world sheet. And you can have one more term that is proportional to the number of handles. So once you write down the path integral expression, so you get the amplitude as. So let me denote the external state by a1 to an if there are n external states. Then, so you have sum over handles running from 0 to infinity with a factor e raised to lambda minus lambda h, and then you have sum over all possible world sheets having h number of handles and a specified number of external states. And then you have the weight factor given by the Polyakov action. Here one should note that I am using the Euclidean spacetime and Euclidean world sheet. So that
this level, of course, you could add additional terms which are non-linear.
that is true, yeah. And then, so we have a summation over all possible world sheets that has particular number of handles in it. So how will you do this summation? To do this summation, we can introduce a metric on the world sheet, and that metric is the one which we use for defining the Polyakov action. So GAB is the metric on world sheet. So you have a sum over matrix.
So you're treating the holes as vertex operators, or
Oh,
you're not keeping track of the holes?
No, I'm thinking of world sheet having holes in it, holes at the asymptotes of the space-time, and then I haven't utilized the state operator correspondence yet. I'm just thinking that
So the number of holes is proven, so therefore you're not talking about that. Right?
yeah, I have chosen how many number of holes that I have, so that's exactly equal to the number of external string states.
But the Euler-Dirichlet formula would not reflect holes or not.
You are saying the number of
Yeah, I mean instead of 2 minus 2,
Yeah, I ca-
there will be an
so that's a common factor, right, which I can always take out. Yeah.
Common factor which comes out of the sum.
Exactly, yeah.
And in the usual way, so if you go with the fact that the vertex operator insertion feed comes with
Exactly, yeah. So you can just renormalize the vertex operator. So that's the basic story. So what we have to understand is a summation over all world sheet metric that we are defining. And this metric is a Riemannian metric. So you can assume that you have a metric d s square on the world sheet, which is written so let me define a metric on the world sheet, a general metric d sigma 1 square 2f d sigma 1 d sigma 2 and g d sigma 2 square. So this is a Riemannian metric on the world sheet. Since I'm able to use a Riemannian metric because I am assuming that my world sheet is Euclidean, then I can do a coordinate, I can define a new coordinate sigma 1 plus I sigma 2. So it's easy to see that in terms of this coordinate, which is a complex coordinate, you can write down this as lambda mod of d sigma mu d sigma bar whole square. So you have defined a complex coordinate on the Riemann on the world sheet. Now, till I haven't defined.
this is a local statement.
Yeah, this is a local statement, right? So sigma 1, sigma 2 itself is a local statement, right?
So you're saying that patch-wise you can put it in this
I
form.
can put it in this form.
Mu is a constant.
Yeah, mu is a function of f, e, f, and g. So it's just a function of sigma 1 and sigma 2, or mu is a function of sigma and c and c bar. It's basically the Beltran
Lambda
definition.
is what? Is also a function.
Yeah, lambda is also a function of c and
Right,
c.
so locally you should be able to put everything up to one core.
I haven't done that rescaling. So because I haven't, so far I haven't claimed that this summation is over all possible Riemann surfaces. I'm just saying that it's the summation over all possible Riemannian metric. Now,
I'm just saying you've not fully used your coordinate.
exactly. I haven't utilized the coordinate invariance at all.
But, oh, mu is a complex function.
Yeah, mu is a complex function. Yeah. So now the point is that if I use this complex coordinate, Polyakov action takes a particular form. Then with that particular form of Polyakov action, you could see that the reparameterization invariants can be thought of as analytic coordinate transformations. So your action, world sheet action, is invariant under all possible analytic local coordinate transformations. So after gauge fixing, you are supposed to perform summation over all possible Riemann surface, all possible two-dimensional surface that has complex coordinate on it, and the Riemann and the surfaces that belongs to the summation should not be connected by any analytic transformation.
Sorry, what was your gauge finally? At some point now you picked coordinate choice. What was your choice of coordinate?
I could use any particular choice of coordinates from that class, and I can say that from that particular choice I could do a coordinate transformation and reach all possible Riemannian metric that I can have, right?
I
So it's
didn't
just a-
understand the statement. So I think that
So
yeah, please, just, did you make a coordinate choice or not?
so far I'm just making a statement that if I use a particular local coordinate c, which could be anything, which could be
so far anything. So far you've got three functions. That's anything.
exactly. So here I'm just making a statement that if I write down my Polyakov action in terms of this coordinate,
Yes.
I can see that the coordinate invariance, the reparameterization that I write in terms of sigma 1 and sigma 2 is just a statement about analytic coordinate transformation.
Well, reparameterization in variance is statement of any coordinate. What? Oh, analytic coordinate changes at the moment, to start with, you've got full reparameterization in there,
Yeah.
which allows you any coordinate change, not necessarily accurate, right?
Yeah, that's true. Yeah. So here,
So what is the statement about the analytic?
so I'm just saying that you could see that the worldsheet action has this kind of a symmetry. So I can take a particular complex coordinate, and if I do an analytic transformation, worldsheet action is going to be invariant.
You're saying, I'm right, you're saying it's while invariant.
Yeah.
And these are going to generate while transformations.
Exactly.
That's where you're leading.
Yeah,
up, right?
yeah,
And so
yeah.
you'll only sum over.
Yes, exactly. So I'm.
Yeah, I think what you're saying is that these coordinate changes, I mean, are a symmetry of the action without changing the metric.
That is true. Yeah. So
Every coordinate change is a change of the action if you also change the metric.
that's true.
These coordinate changes are change the symmetry of the action without changing. That's it.
Yeah. So the statement is that I just started with a sum over all possible worldsheets, and I just want to claim that the sum over all possible worldsheets can be thought of as sum over all possible Riemann surfaces. So that's the only statement I want to make.
I just to understand your logical flow, since you're saying it so in such a first principles way, I didn't understand why you focused on the sum over Riemann surface.
Here, right? So I have a expression for string amplitude, which is written as sum over all possible metrics plus I have a path integral inside the sum over all possible metric, right? So I have a path integral for the embedding coordinate.
See, somewhere you need the statement that worldsheets that are generated by different while factors
Yeah.
are actually the same worldsheet.
Yeah.
You need to make that statement.
Exactly.
I think you said that.
Yeah. So actually, I just want to say that I have to start with. I have infinite number of possible worldsheets, but after taking care of the symmetry of the Polyakov action, I had to do a gauge fixing, and I had to choose only a class of worldsheets out of this all possible worldsheets, right? I could have several worldsheets having different kinds of coordinates, right? With different kinds of complex coordinates, which could be connected by some analytic transformations, right?
But somewhere you want to say that that different coordinate systems that are the same complex system but differ by a while factor
Yeah.
actually are the same physical configuration.
That's true. Exactly.
That statement needs to be there somewhere.
Exactly.
Okay.
So that's the only statement which I want to make. So here, so far I started with just a surface with Riemannian metric on it. Now I want to have a particular mathematical structure on the worldsheet that I am considering. So the mathematical structure that I want is that I should have a complex structure on the worldsheet. So it's a particular class of surfaces, right?
So there's an additional physics input that is wrong in here.
Yeah.
For example, the while anomaly has to be coupled. So you are in the critical dimension.
I am in the critical dimension.
Etc.
Yeah.
Okay.
So I don't want to introduce any Liouville fields in it. So I am looking into a critical string theory where I am specifying a particular dimension for the target spacetime. And then given that all condition, the sum over all possible Riemannian worldsheets reduces to sum over all possible Riemann surfaces. That means a surface, a two-dimensional surface that has a complex structure on it.
Sorry, I should notice that in 2 dimensions, let's say we take closed surfaces, they don't all admit a complex structure.
Yeah, if it is orientable, they will admit a complex structure.
Orientable.
You have non-orientable Riemann surface also. But this is a structure that you can always introduce in any two-dimensional
Locally,
surface.
they always admit a complex.
Exactly. Yeah.
Globally,
Yeah.
So the closed field case, we need some over those with a complex structure.
Exactly. Yeah. So I just made the statement that I have to sum over all possible worldsheets on which I can introduce a complex structure. So I haven't told you what is a complex structure. What do I mean by a complex structure? I know that many of the statements are known for many of you, but I just want to make sure that I'm not missing anything.
I might be anticipating, but I mean, in higher dimensions or in the context of Calabi-Yau and so on, the obstruction is that the
Right.
Nagelius tensor or whatever has
Yeah,
to
vanish.
Is a similar thing which is not automatic in 2D.
In 2D, I mean,
That's why I was
it's
thinking-
always possible. The statement that you made is true. I mean, if I assume that I have a worldsheet that is orientable, then I can always introduce a complex structure on it. If it is, yeah.
And
If
that's
I-
global.
It's a global statement.
Locally, there's no.
Locally, you can always introduce. You can introduce a complex structure.
Is it okay?
So, So I was just trying. So my main motivation for discussing this was that I have to study the theory of Riemann surfaces if I want to study string perturbation theory in full detail. So that's the reason why I was going through these known facts. So let me discuss the basic features about Riemann surface.
See, one thing, just to summarize what you said about Riemann surface.
Yeah.
If I understand you right, you said locally everything is a Riemann surface. If you plus a y factor,
Yeah.
the y factor doesn't matter. You only care about it.
Yeah, that is true.
But fine.
Yeah, these two pictures are actually same. I mean, the things that you can relate by Weyl factor, Weyl transformations, or I mean, this notion about complex structure. They have a one-to-one correspondence. So either you could think in terms of complex structure, or you could think in terms of metric. So the thing that you are talking is actually you are thinking in terms of metric. So here I just mentioned a complex structure. I don't have to really talk about a metric. So these are two pictures. Either you use metric picture or you use the complex structure picture. So what is a Riemann surface? A Riemann surface can be intuitively understood as a collection of domains that belongs to a complex, different complex planes. And then, so you have a set of domains ui. And then the first condition is that the surface that you want to describe must be thought of as collection of several domains ui. So the union of all these domains must give you the full surface. Now, since you have different patches, you should know how to glue these two different patches. So in each patch, you can define a coordinate. So in the patch ui, you have a coordinate ci. So what it does is, from the Riemann surface, so you have several patches. This patch I call as ui. So you could define a coordinate that maps you to a region inside the complex plane. And then you could consider another patch. Again, you can map this patch to a complex plane with coordinate cj. So far I haven't said, I mean, this is something which you can always do. Now the thing that makes it's a Riemann surface is the following fact: how you really glue these patches. So you have coordinate ci on ui patch. Assume that the patch ui and uj has an intersection. Then the coordinates ui defined in the patch ua and the coordinate defined in the patch uj can be related to each other inside this region where you have intersection. So in this region, you could find a mapping that relates ci coordinates and the cj coordinate. Similarly, you could define a mapping that connects cj to ci. The condition is that this map G must be biholomorphic, or the map G and its inverse must be holomorphic. So you have a coordinate transformation that is holomorphic. So if you are able to find such set of domains and such kind of transition functions, you are actually looking into a Riemann surface. So this is what you mean by a Riemann surface. And the complex structure on the Riemann surface means the collection of all domains and the complex coordinate in it.
Hi, can you hear us? HRI?
Yes, you can.
Okay. Some other ICTS? Oh, we can disconnect that actually.
ICTS, can you hear us?
Is there anybody? Oh. ICTS, can you hear us?
There is 3 people. The 3 people.
They raised their hand. Right?
So, I think you should say decline.
Somebody is hearing it.
What is the ring? Is it a third party? I think.
I think they are disconnected temporarily, right?
But apparently they said yes, it is yes.
Well, that's the case. Oh.
ICTS is probably muted, that's why you can't hear.
So this is the definition of a Riemann surface. Let me give you some examples of Riemann surface. So any domain in a complex plane D with coordinate C is a Riemann surface, and the complex structure of that domain D is this set itself, domain and the complex coordinate C. And now you have more non-trivial example, that's a Riemann sphere, so which is a complex plane with infinity in it. And here you have to define local you need two patches to define a complex structure. So you have Riemann sphere, so you have south pole and north pole here. So the thing is that you could choose two patches, one complex plane itself with complex coordinate Z, and the Riemann sphere minus 0 with 1 by Cs is local coordinate. So you have a complex structure which has two domains in it. So this is an example of non-trivial Riemann surface.
Right, and so suppose you try to put the usual round sphere metric on
Yeah.
the Riemann sphere,
Yeah,
and I wrote it in terms of your first complex patch times the Weil factor.
yeah.
The problem will be that the Weil factor will go to infinity
At the
at that row.
yeah, that's true. Yeah. So that's the reason why you want the two
So you
patches.
have many, from the Weil function point of view, Weil function is not allowed to go to either 0 or infinity.
Exactly.
Where it goes to 0 infinity, you put a new patch.
Exactly. Yeah. So you want the metric to be finite. You don't want singularities in the metric. So this is the basic definition of Riemann surface and some examples of Riemann surface. Now let's go back to string theory. So we said that you have a definition of amplitude, H loop contribution to an amplitude with n external state, and that is that we should think of as sum over all possible Riemann surfaces that has H handles and n number of asymptotic boundaries. So I should say that an asymptotic boundary in the Riemann surface language can be thought of as a puncture. So you have different ways of representing a Riemann surface. You could think of a Riemann surface with long cylinders attached to it. So if I do a uniformization to complex plane, these long cylinders will map to a puncture on it, puncture on the complex plane. So a Riemann surface with puncture and a Riemann surface with
Uniformization with complex. Explain those words, please.
I will explain. Yeah. So if I could think of, so I said that, so the basic picture is the following. So let's consider a interaction of 4 external string at with 0 handles. Here I could think of this external state as a long cylinder, right? Now I could do a mapping from this picture to the complex plane, to the extended complex plane. So when I do this mapping, so these are two representations of same Riemann surface, right? So you could find a function analytic or conformal mapping from this picture to the complex plane picture. So
With many singularities.
with singularities, right? So those singularities are the 4 functions.
No, those are the singularities associated with functions. Say this had some high genus, you would be able to, there would be singularities above.
So you want, so that's true. So this is, so if you don't have any handles, you could directly map it to extended complex plane. So if you have some handles in it, you won't be able to do that. So you have to add further identifications.
So you're doing this basically locally, which is, right?
Yeah. So here I can do it globally. If I don't have any,
in general, you will do it locally.
Locally.
Part of this and
Exactly.
then-
That is true. So this, when I say uniformization, I'm just saying that I could find a mapping,
You
conformal
cut it,
mapping.
You cut the thing, keep the part, keep the infinite part,
Exactly.
and add that to a disk.
Exactly. Yeah. So that's what I mean by uniformization. So an asymptotic.
Uniformization just means the map that takes you locally to the complex plane, or just
I mean, I will explain you that detail a little better.
So far, it sounds to me that it's a map that takes you to a disk.
To a disk, exactly. A long tube can also
Cut it
always,
somewhere, including the long tube, and that whole thing takes you to it.
yeah.
It's the state of data.
a state operator mapping. So here, if I mean the point is that you could think start from the complex plane and introduce a metric here, and this picture I am visualizing from the point of view of metric. So you are trying to draw geodesics, and the geodesic that goes to the puncture will take infinite time to reach there. So that's what I mean by long external cylinder, right? So that's why you could think of a Riemann surface with external spring status, Riemann surface with long tubes attached to it, or as a puncture. So here I will go. I will go from one picture to other without really mentioning it. So the point.
So just to be sure, then you're cutting it only a region which has only one of the cylinders.
Yeah, yeah.
Because otherwise, I mean, even if it has two cylinders, I don't know how to do it.
So the point is that here you don't have to really do the cutting. You could directly find a mapping, which is not a local statement. You can find a global statement that you have a mapping, a conformal mapping, which take you from this picture to a complex plane with some number of punctures.
For instance, that mapping, even for a case of a sphere, will have one irregular point.
Yeah,
Because a sphere cannot map to a plane without a singularity.
that is true. So you are just introducing.
So, but in your notion of mapping, if you allow singularities,
Yeah.
you can allow many things. Don't you want to make this a local sphere?
No, the point is that when I say that there is a singularity, I'm just supposed to not include that particular point in the complex plane, right?
One singularity, I can allow others. And once you start allowing singularities, you'll have to specify what kind of singularities you allow and so on. I don't. What do you want? I mean, it sounds to me like you want to make a simple local statement. Why do you want to do something global for that?
I mean, because this is something which you can do. I can write down explicit functions which does this.
With zillions of singularities. Suppose you have a genus H, genus G surface, you'll have G singularities or something like that.
And you want that this map should be holomorphic on the.
Singularities, then you'll have to give us a theory of your singularities.
Yeah, one can do that. So you could introduce singularities like elliptic singularities or whatever you want in this for this.
I thought to begin with you were at h equal to 0.
Yeah. Yeah, h is equal to 0. Yeah.
But you want to do this for all string
But I think in this case, this is the point that you take map it on the complex plane, and then at infinity you use the same prescription that you use 1 over t as a coordinate,
That's true.
and that's the map, right?
That is true. Yeah.
But suppose we wanted to do this for a genus G Riemann surface, then you'd have to extend that notion.
Yeah, here actually this picture will change. You have to make some identification.
That's true. You have to do identifications.
Okay.
So
You still want to map it globally onto the complex plane, but after some identification,
exactly.
you have to convert it to genus G.
That is true. That's true. Yeah. So anywhere.
In this case, it does.
What?
In this case, it does D goes. In this case, it
Yeah.
does D goes to 1 over t that you have to do identification.
Exactly. That's true.
So with one prescribed singularity of a prescribed form.
Yeah. Yeah. So if I choose that the punctures are at 0, 1 and infinity, the infinity point is already removed out, thrown out. So you don't have to use two patches. You can always use single patch, right? And then find a mapping. So at the end, what you are supposed to do for computing H-loop amplitude in, say, bosonic string theory is that you have to perform a sum over all possible Riemann surface that has H number of handles and n number of punctures in it. So such a space is called moduli space. This is a moduli space of Riemann surface with H number of handles and n punctures. So see, since this moduli space is a continuous space, you could remove or you could replace the summation with an integration. Now what will you integrate over a moduli space? You integrate a differential form defined on the moduli space, right?
I haven't understood your definition.
Okay.
of moduli.
Yeah.
So when are two things different?
Okay, actually I didn't say this. I should say it. So I just said that I have Riemann surfaces. I didn't really tell you. I explained the notion of complex structure on a Riemann surface. I didn't tell you when two Riemann surfaces can be equal with, or when can I identify two complex structures. This is something which I didn't explain. So let me explain that. So equivalence of complex structures. So consider two Riemann surfaces R with complex structure Uj, Cj, and another Riemann surface with complex structure Vj, Wj. So we say that these two complex structures are same if you are able to find a holomorphic or biholomorphic map between these two domains that relates the coordinates Wi and Ci. So if you are able to find a biholomorphic map between each patches of the two Riemann surface that provide you the complex structure, then you are then what we say that these two Riemann surfaces are actually not two different Riemann surfaces. They are actually different representations of the same Riemann surface.
This is a local statement.
So yeah, for all patches you can do it. So when you say that all patches, you are actually making a global statement, right?
I'm sorry, so the index set is the same, I mean the number of charts.
So I'm just, for simplicity, I'm assuming that there are equal number of charts, right? So what I could do is I could choose different number of charts, and then I have to deal with, all. This is something which I can do. Like then I have to split the chart, different domains into two pieces, so that I can make the number of charts same.
You can choose charts
In
that
this way.
there is
There is an
a
equal. Exactly.
And
Here I haven't. Oh, okay. Yeah, there is a statement about.
so this is the identification that takes you from the upper half plane to fundamental domain in case program.
So I haven't come to that picture yet, but here I'm just.
So far he was going small.
But it is the equivalence of complex structure.
Yeah, equivalence of complex structure have that notion also. So that means how I define my, I could choose big patches, and then I could do something more to make it a large diffeomorphism. But the statement of equivalence of complex structures includes small diffeos and large diffeos.
So does this definition take into account the presence of poles and handles in the structures?
Yeah. So that's why I had to use so many domains. So this
And the positions of your vertex operators,
punctures, right? So
punctures also have to be the same.
exactly. So you should have same number of handles and you should have same number of punctures.
And
Then you could
and the same position.
positions,
Two
right?
things are equal if you can make such a map
Yeah.
such that after you made it,
Exactly.
the positions of the vertex operators are
True, because you are thinking of that as one parameter that varies the Riemann surfaces, right?
I think this might be a trivial question. If I take a Riemann structure with angle h1 and S and another Riemann structure and
H2.
H2,
Yeah, then I won't be able to find them.
then this can never be able to do.
I won't be able to do it. Yeah,
This is like a
that's a statement because that's a topological statement. If the number of punctures and number of handles are different, then definitely I won't be able to find a mapping. Even if I have same number of handles and same number of punctures, still I will be able to define different Riemann surfaces having different complex structures. So that's why, even though I restricted in this particular case, I already chose. I have chosen how many number of handles that I want, how many number of punctures that I want. Within that class, still I will be able to find infinite number of Riemann surfaces, and the set and those Riemann surfaces have complex structures that are not equivalent under this identification.
Usually when one says complex structure, one already model out by this.
Yeah, that's true. So that's why when you say complex structure, you mean the equivalence class, and then choose a particular representation. So you have we end up with this statement that you have an H loop contribution to string amplitude, which can be thought of as an integral over the moduli space of Riemann surfaces with H number of handles and N number of punctures. So when you say that you are performing an integration over moduli space, that means you are actually integrating an object that you defined inside the moduli space. These are the differential forms, right? So you have to consider a top form defined in the moduli space of Riemann surfaces with H number of handles and N number of punctures. And then this and the point is that this is not completely, since we have some physical inputs, you have to say that this differential form must be depending on the external state that you are using for computing the external state that are involved in the scattering process. So you have a differential form defined in the moduli space, but how you construct the differential form is another story. So that is the basic thing that we do in string perturbation theory. We are giving or finding rules for constructing a top form in the moduli space of Riemann MHN using our knowledge about CFT.
Top form which is normalized in some way because the top form
but the rules of string theory defines what exactly is those normalization. So so this is not some random top form. This is a top form which you constructed using the principles of string theory. So you don't need any further normalization. Actually you don't have to look into those statements. So when I'm using the theory of moduli space to construct this form, then I have to make sure that this top form has appropriate factorization to figure out the normalization factors. Since I am constructing it from first principle, I don't have to I don't have to worry about any normalization factor. Everything comes with it. And this object will naturally factorize.
So is this typical one doesn't really worry about the volume of the object of this amplification?
You mean the equivalence of, that's already there in the statement. Since I'm integrating only over the moduli space.
The volume of each object is taken to the same.
Exactly. So I have done that gauge fixing. That's how I end up in moduli space. Right? Here I already I already taken care of small differes and large differes. I don't have.
Maybe this is not a relevant question, but what I was asking was that for a given complex structure,
Yeah.
its equivalence class will be taken from one of the complex structures equivalence class.
Yeah.
So this will contribute more, this will contribute less. That kind of thing is not.
So that's already taken care in this form itself, right? It's a form that knows all those details. So I'm defining a form at a particular point in the moduli space. When I vary that particular base point, the form of this object will change, right? So that by that I mean this form knows about all those details.
But in the standard way of doing this, it's the ghost which takes care of the volume.
Ghost.
The ghost and the anti.
So that's the next point. So we have to. I just told you that the structure of amplitude is of this form. I haven't told you how to construct this top form for particular amplitude. So that's the next goal.
U1 to AN are denoting the vertex vector, right?
Yeah, they are denoting the external states. So that means if you really want to understand string theory, or if you want to construct the integrand or a string measure, we should know more about the geometry of the moduli space. So let us start asking the understanding. Let us try to understand what is the moduli space of Riemann surfaces. So the simple case is that you have Riemann surfaces that are simply connected. What is a simply connected surface? So a simply connected region means you can consider a region and consider all possible loops in it, and all these loops has the property that you can shrink them to a point without crossing any further singularities or anything. So such regions are called simply connected regions. So we are for the moment looking into only those Riemann surfaces that are simply connected. Now the uniformization theorem states that there is a theorem which I won't be able to prove, or I don't even try to prove. Uniformization theorem states that all simply connected Riemann surfaces are biholomorphically equivalent to three possible Riemann surfaces. These are the complex plane itself, and the extended complex plane or Riemann sphere, and the upper half plane. So you have only these three surfaces when you say that your Riemann surface is simply connected. Any other Riemann surface which look different from these three classes can be brought to this form. You can always find a conformal map which can take any simply connected Riemann surface to either C, either complex plane or Riemann sphere or upper half plane.
Here this loop that you were talking about is something which does not include a puncture. Right?
Yeah, so anyway, when you have a puncture, it's not simply connected. When I have a puncture there, it's not a simply connected thing, right? Because I could always find a
I see. Now you're talking about surfaces without any puncture.
without any puncture. That's what I'm just here. I was trying to define what do I mean by simply connected regions.
Just repeat this last thing you said about, so you have a simply connected Riemann.
Yeah, if I have a simply connected Riemann surface, I can always find a mapping, conformal mapping, that can take the surface to either complex plane or Riemann sphere or to a upper half plane. So that means when you are looking into this restricted class of Riemann surface, you have only 3 possibilities. So the moduli space of simply connected Riemann surfaces are trivial. You don't really have any non-trivial moduli space.
Another way of taking Riemann sphere is that you can always find a constant solution metric.
Exactly. So these are the 2 pictures. Either you think in terms of complex structure or you think in terms of metric. So these 2 are same story. Actually, I am.
Why are these two the same as simply connected?
Because if it's constant solution metric, then these are the 3.
First of all, you won't be able to find a constant curvature metric for this.
Sorry?
So when you say that you have a constant curvature metric, you are basically saying that you can find a hyperbolic complex plane. That's not true.
Sorry?
You don't have a simply connected hyperbolic surface. A surface is hyperbolic metric in it.
That's statement of the
Yeah, for genus 2 without puncture, that's a hyperbolic surface. Or if you have 3 punctures on a complex plane, that's a hyperbolic metric. You can map it to a hyperbolic metric. So you can't make that statement for the these cases, simply connected Riemann surface. You at least need either you need a puncture or enough number of genuses to introduce a hyperbolic metric on it. Yeah, by that I mean you won't be able to find simply connected Riemann surfaces which has different complex structures, or a simply connected Riemann surface has complex structure which is exactly equal to these 3.
But are these 3 equivalent?
No, these 3 are not equivalent. So these are, so by that, so you have simply connected Riemann surface which has a moduli space that is given by 3 points. So that's what I mean by. Oh yeah, that's true. Yeah. So maybe I think I made a wrong statement there. Here I have a boundary, right? Upper half plane has a boundary. It's actually the boundary that makes it a hyperbolic surface. It's still simply connected. So that's one wrong example. So Riemann sphere don't have any hyperbolic metric on it, or complex plane don't have. The presence of boundary is the thing which makes it. So that's the main story. So when you compute the Euler characteristic, it should be less than -1, or less than or equal to -1. It has Euler characteristic -1.
So even if the surface is not simply connected,
Yeah.
there's still a theorem that says that one can find a constant curvature metric.
Yeah, that's my next topic. So we saw one particular class of Riemann surfaces which are extremely useful for understanding multiply connected Riemann surfaces. So when you have multiply connected Riemann surface, you see that there are closed curves which can't be shrink to a point. So in that situation, you have a bit more. You have more possibilities. To understand the moduli space of multiply connected Riemann surface, it's very useful to introduce a notion of covering, universal covering.
But when you regard the complex plane as a Riemann surface,
Yeah.
how is the boundary, how is infinity being thought of?
You can think of it like a disk with infinite radius.
The complex plane is the same as a disk.
Disk with infinite, yeah. Yeah. To get Riemann sphere, right?
Because but he's distinguishing between C and C hat.
Yeah, so these are 2.
C hat was the guy with the compactification.
Exactly.
But he's treating C as a separate manifold. right?
Exactly, yeah. So
Yeah.
Yeah.
Something like C.
it's like an open disk with infinite radius. Yeah, that's true. With finite disk.
C is not compact.
Any disk, yeah, any unit disk that has finite radius can be mapped to a upper half plane.
I think Naveen has said it very nice. There's an open disk, a closed disk, and a disk.
Exactly.
Like an open set, a closed set, and a disk. A disk which is an open set, a disk which is a closed set.
So the open is C, the closed is A-dish.
Exactly. Yeah, this is non-compact. Exactly. So C Riemann sphere is a compact surface. C is a non-compact surface. So that's the main difference. That's true.
So Naveen had this nice formulation. You agree with it? That C should be thought of as a disk
With
which is an open set.
exactly
C hat is a sphere and H is a disk, which is a closed.
close it. That's true. Yeah. So these are different way of thinking the same. Yeah.
Does something already go down if you consider a high dimensional what is the high dimensional object?
You mean high dimensional manifolds, right? I mean, first of all, I won't be able to. There you have. I mean, are you thinking about complex manifolds?
Spheres with punctures.
Sphere with punctures.
Now you would have
I don't know whether there exists as uniformization theorem for high dimension. It, I don't even expect. Yeah. So to understand the moduli space of multiply connected Riemann surface, it's important to introduce this notion of universal covering. So let's consider two Riemann surfaces R and R tilde. Now assume that there exists a mapping phi that takes you from R tilde to R. So you have two Riemann surface and the complex structure of R and R tilde could be extremely different. You could even have situation where R tilde has one particular genus and R has some different number of handles. So these R and R tilde are those surfaces which may not be topologically equivalent. So you consider two such Riemann surfaces R and R tilde, then if you are able to find a mapping from R tilde to R with the following property, that this map takes a domain U of R tilde. You have a domain V in R tilde that is mapped to U. So this mapping is not one-to-one. But if I restrict to inverse image of a particular region in particular domain in the Riemann surface R, which I denote by pi inverse U, you could find so many disconnected domains. And if I restrict this inverse domain to a particular connected domain V, then within that connected domain, this mapping is biholomorphically equivalent. Yeah, that's true. Yeah, to make it universal covering.
Just say once again, so your two Riemann surfaces R and R.
R tilde, which could be extremely different, with different number of handles or with different number of punctures. And then I'm just trying to find a mapping that takes R tilde to R. If I succeed in that business, then I could see what is the inverse image of a particular region in R tilde. So the statement is that a particular domain in R might have different disconnected domains in R tilde. Now I can restrict the map to a particular connected domain in R tilde. Then in that restricted domains, the mapping pi must be biholomorphically equivalent mapping. So it should be biholomorphic mapping in that particular domain. So first of all, this pi is not one-to-one. Now you can restrict the domains of R tilde such that pi can be made to be one-to-one. When I do that, that mapping must be biholomorphically equivalent.
Pi holomorphic inverse?
Holomorphic,
Inverse and
inverse and the function should be holomorphic. So that's what I mean by a covering transformation. So you have a covering.
So in this case, you say R tilde has covering of R.
Exactly. R tilde is the covering space of R under this map pi. Now I can assume further that R tilde is a simply connected Riemann surface. Assume that R tilde is a simply connected Riemann surface. Then the pair R tilde pi R is known as universal covering. So the idea will become clear when I say some examples. So you have a mapping from simply connected domains to any Riemann surface. There is a mapping, and that kind of a mapping is known as universal mapping. So you have a universal covering, which is a pair of two Riemann surfaces and a particular mapping. So
The multiplicity of pi inverse is like discrete.
it's discrete. Yeah, it's countable, right?
And if it is, if it is not many to one, I will
Exactly. Yeah, that's true. So you could think of a mapping which takes C hat to C. So a holomorphic mapping or a biholomorphic mapping is a special case of covering mapping. It's actually a trivial covering map. So that means you will be able to connect any Riemann surface to complex plane or Riemann sphere or upper half plane. So
Give us an example.
I will give, right now I am going to give an example. So actually I will come to the exactly. So one example is the following. So maybe before going to the example, I have to introduce one more notion. There's the notion of covering group. So this looks a bit dry, but these are very extremely useful in studying the theory of moduli spaces, which are necessary for constructing this top form. So you can start. You have a pair R tilde, pi, and R. This is a universal covering. Now assume that there exists a transformation inside this simply connected space. So you have a point C belongs to R tilde. You could find a mapping gamma of C that takes you to another point in R tilde. Now if pi under the covering map, pi of gamma is exactly equal to pi, then you call that particular transformation gamma as covering transformation. So with respect to the covering map, gamma looks like an identity.
So it takes you to another point which has the same.
Same image. Right.
So let's say this is Z2 thing, it takes you to the Z2 transform.
Exactly. That's true. So if I consider all such
It would be like a 2 pi rotation.
exactly. So if I so basically that's the reason you can connect this covering transformation to the homotopy. So you could consider all possible these covering transformation. They form the covering group. So gamma forms the covering group. Now why I am interested in this covering group? The reason is that then I can think of R as a quotient of R tilde with this covering group gamma. So now I can give you examples. So I introduced the notion of covering, universal covering, covering map, universal covering surface, and then I introduce this notion of covering transformation. Then we can easily see that the covering transformation forms a group, and it is a covering group. Now you can use the covering group to obtain the Riemann surface of our interest from the simply connected Riemann surface R tilde.
And does this gamma have some property? Does it preserve the complex structure or something?
I mean, you can.
No, I was going to say, I assume different elements of
Gamma.
will correspond to different choices of
Complex structure. So in
plane modeled by SL2Z is the torus.
exactly. So gamma. Yeah. 2 pi. Yeah. Yeah. Exactly. Trivial. Yeah. Exactly. Yeah. It's exactly the covering group. It's exactly the covering group. So the question that Shiraz was asking.
Complex structure, something should be preserved so that you can identify with other things.
Yeah.
That's my theory.
Equivalent complex structures for higher genus surfaces will be related to
The covering.
these things up to these mappings.
Exactly. So the what we are gaining of through all this discussion is that we said that we have inequivalent complex structures for higher genus surface with some number of punctures, right? Now we are connecting that particular Riemann surface to a simply connected Riemann surface plus a identification using covering group, right? Now what we are gaining is that we are dumping all the information about complex structure of R into the covering transformation. So covering transformation or covering group will know everything about the target Riemann surface. So that's a good thing that we are going to gain.
Probably if Artinda is simply connected, there's no issue of the system. You will go from
So-
Let's just say every point, so thinking of the stereographic projection.
Yeah.
So every point on the complex plane has two images on the sphere.
Yeah, that's good.
And so gamma in that case is.
So the I mean the Riemann sphere itself is a simply connected thing,
just infinity is already.
but still I can find a mapping like exponential map which can take you from Riemann sphere to a complex plane, right? Yeah. So let me give you an example which will make everything clear.
The idea is to get simply.
Simply connected surface, right?
But that will be very similar from the Riemann sphere to the complex plane.
Yeah, it's a singular map. Actually, it doesn't matter. Yeah, let me give you an example. So you could consider this mapping. So you have a complex plane mapped to complex plane removed with zero removed from it. So you can map from complex plane to complex plane with without origin in it. So the mapping is given by phi of c equal to e raised to c. So this exponential map will provide you this covering transformation. So you see that this object is a simply connected surface. Now here you have a multiply connected surface, and the covering transformation is c going to c plus 2 pi I. So this forms a nice U1 group. Right? This U1 is the covering group. So if I take start from complex plane and mod out by U1, that will provide me complex plane with zero center removed from it. So this gives you an idea how a covering group is doing the whole nice thing. So you can go from simply connected to multiply connected surface, and all the information about the complex structure of the target space will be encoded in the covering transformation. So that's a nice thing. So
I'm sorry, you can choose different complex structures in C mod, C minus 0.
yeah,
And they correspond in 1 to 1.
yeah,
Corresponding to the element of U.
exactly. That's true.
So that's not the covering group for scientific.
Yeah, CN, it looks like CN, isn't it? I mean,
Yeah, this is CN, right?
not you, just CN.
Oh, C.
Sorry,
I
sorry,
see.
Z.
2 pi I N. He actually Z goes to Z plus
So,
N.
2 pi n. Right. Yeah, that's true. Yeah, in this case it's not U1 actually, C. That's
It's clearer if you look at that. I'm sure it's like a
That's true. Yeah. So you have an infinite cylinder with infinite length. So that tells you about the basic idea of covering transformation. Now we are going to utilize this property for understanding multiply connected Riemann surface. So let me repeat why I am doing this. I am trying to understand the moduli space of multiply connected Riemann surface, and I should find a particular way of characterizing the moduli space and characterizing the tangent space of moduli space. Everything I should get a clear hold. So now I am going to explain you something called Fuchsian model of a Riemann surface, which is related to hyperbolic Riemann surface, which admits hyperbolic metric only. So if you are interested in Riemann surfaces that can't be connected, or that is not biholomorphically equivalent to complex plane or C bar minus x minus 0 or tori C hat. If I am not interested in this kind of Riemann surface, which usually mathematicians call as exceptional Riemann surfaces, then I can enter a hyperbolic metric on it. By that, what I mean is I can compute the Gaussian curvature at every point on the Riemann surface. That should be equal to -1. A Gaussian curvature is half of the Ricci scalar. So if I compute, so this metric is extremely symmetric metric. So if that Riemann surface admits a hyperbolic metric on it, then I can construct a Fuchsian model.
Sorry, I was taking a hyperbolic metric for constant curvature.
Yeah, with -1 constant curvature. So for every hyperbolic, so such Riemann surfaces which admits hyperbolic metric, I call them as hyperbolic Riemann surfaces. So every hyperbolic Riemann surface has a Fuchsian model. I will explain what do I mean by Fuchsian model. It's related to the covering group that I was describing. So let me consider a Riemann surface R. When R is not an exceptional Riemann surface, then R can be thought of as a surface that is obtained from upper half plane divided by a specific group which I call as Fuchsian group. So I haven't told you what exactly is Fuchsian group. So let me start with a hyperbolic with an upper half plane, and then somehow I can find a group which does identifications in the upper half plane that will correspond to a particular Riemann surface. So to understand this idea better, let me introduce a metric on the upper half plane. This is the Poincare metric. On the upper half plane, I am introducing a metric that has constant curvature -1, Gaussian curvature -1 all over. So the metric is dSH square equal to dC square divided by imaginary part of C all square. So you have an upper half plane with Poincare metric on it. Then this metric has a symmetry. So if I consider a transformation C to gamma C, which is given by a real Mobius transformation, with A, B, C, D all belongs to real number, and then AD minus BC must be equal to 1. So such transformations form a group PSL2R. So this is the diffeomorphism group of Poincare metric defined on an upper half plane. Now one can consider a subgroup of a normal subgroup of PSL2R. Then let me denote that subgroup as gamma. Now I can identify upper half plane using a subgroup of PSL2R. Now what Fuchsian uniformization theorem state is the following. If the Riemann surface is not of an exceptional Riemann surface, then you can always find a subgroup of PSL2R that generates the Riemann surface R from upper half plane by using the idea of covering transformations. So you can start with upper half plane with Poincare metric on it, and then identify points on the upper half plane under the action of a subgroup gamma. Since gamma preserved the metric on the upper half plane, the Riemann surface that we obtain by doing this quotienting also will have a metric that has constant curvature -1 on it. So this provides you a model for hyperbolic Riemann surfaces.
And in fact, will also always have this metric.
Always with this metric, exactly. So you have constant curvature -1.
Now it's important that you're modeling out by something that's an isometric.
That's an
You get a
isometric.
singularity.
Exactly. So we won't get any singularity, or we don't have any orbifold points. Yeah, exactly. And the different complex structures. In fact, not precisely the different Riemann surface. There will be further identification for Fuchsian due to the mapping clusters, which I will explain. So at least the basic idea is that we have all different possible classes of hyperbolic Riemann surfaces with different complex structure on it. Now we are dumping all the information about the complex structure of a hyperbolic Riemann surface into this Fuchsian group. So Fuchsian group consists of 4 real numbers, right? So you have a transformation gamma which take you to AC plus B by CC plus D. So this provides me 3 independent parameters. I can vary this independent parameter, or I can vary this group structure to get different kinds of hyperbolic Riemann surfaces. So all information about the moduli space of Riemann surface can be thought of as the possible classes of Fuchsian group that I can have. So that's why it's extremely powerful. Now we get a hold on the subject. So now here we said that we have this notion of covering transformation. So every element of covering group corresponds to an identification on the Riemann surface R, right? Yeah, exactly. Yeah, that's true. I'm exactly. Exactly. That's why I get the P. That is true. So I have further redundancies there. I just want to fix those redundancies.
And topological information like the number of handles or the number of punctures must be somehow stored in A, B, and C.
Not in A, B, C. It's actually stored in the group gamma itself. What is the rank of this group, right? What
Gamma is determined by what choice of.
exactly? You could have several number of elements, right?
Or what I meant was by the choice of gamma.
Exactly, exactly. By the choice of this capital gamma, I can vary the number of handles and I can vary the number of punctures. It depends on which elements of what are the elements of gamma.
Very nice classification of what subgroups it
Exactly.
must be beautiful.
It's actually an extremely beautiful subject where, this is one particular topic in mathematics where I could see explicit calculation. They don't really utilize any big statements about homotopy or homology. They do just calculations using cos hyperbolic functions, sine theta, which looks very nice.
I'm confused by the condition AB minus BC equal to 1 as well as P. So if you say PSL2R, then don't put that stuff. That's just a representation of.
Exactly. I just said that I came through this way. So I have a transformation of this kind.
And AB minus BC equal to 1 is a particular gauge.
Yeah. That's yeah.
P is what you need. You don't need AB minus BC equal to 1. Otherwise it's redundant.
That's true. Yep. Yes. So once I mention that A, B, C, D belongs to PSL2R, then I don't have to specify extra conditions, right? So that's what you're saying. It's just a matter of nomenclature.
Yeah, that if ABCD appears only in this kind of relation,
So
then clearly they are defined up to scaling, and that scaling means that it's
PSL2R, yeah.
which can be chosen by using the determinant condition.
That is true. Yeah, this is basically determinant condition, right?
Yeah.
So now, now the next observation is that every element that belongs to this Fuchsian group gamma corresponds to a simple closed geodesic on the Riemann surface. So let us consider genus 2 Riemann surface. Riemann surface is 2 handles. This is a hyperbolic surface. I can consider different geodesics with respect to the hyperbolic metric that I defined on R. So this geodesic, when I call it as a simple closed geodesic when the geodesic is not intersecting to itself.
So you're not going to give us some sense of what the subgroups of this SL2 are?
Yeah, so I could consider something like gamma 2, which corresponds to transformation C going to minus 1 by C and C going to C plus 2. So I can consider a specific subgroup. So if I use gamma 2, then H by gamma 2 provides me thrice punctured sphere. This is an example of Fuchsian uniformization. So here you see that I fixed there is no leftover parameters.
But I just want to see, there must be a classification of these subgroups which is labeled by effectively genus and number.
Well, that's what I was asking.
Yeah, so that's the next story.
Okay.
Embedding of that into this model.
Yeah.
And there's probably still further equivalences, right?
No, actually you don't require any further equivalence. This group, this particular surface itself has enough number of handles, depending on how I choose gamma. So I choose gamma 2. If I choose this kind of identification, I won't get any handles. I will just get 3 punctures. Now I can change gamma 2 to something else, so that I can get a hyperbolic Riemann surface with 4 borders instead of 4 punctures.
Do you mind with one basic example, just showing us where the location of the singularity is?
So you want the fundamental domain, how the fundamental domain looks like, right?
Yeah, I just want to see you go from modeling this out. to
Yeah.
something I
So
already-
so let me explain you that. So I have this identification on the upper half plane, c going to c plus 2 and c going to minus 1 by c, right? So let me start with the first identification, c going to minus 1 by c. So it's equivalent to saying that every point inside a unit circle will be mapped to yeah. If I just do some appropriate shifting, so this will go to every point inside will go to a point in the outside, right? Now I have further identification c going to c plus 2.
Wait, will the circle centered around 0?
Yeah, I could think of it like 0, 1, 2. Sorry, 0 and 1. I could do similar.
I did not. So shifting by 2 will shift to the circle centered around 2.
That's true. I could start from this picture where I have 0, right? This should be true, right?
Okay.
Now I have to do further identification, c going to c plus 2,
Yeah.
right? So if I do this identification, what I get is the fundamental domain looks like this.
Wait, at the first step you said that everything inside the circle is equal to the
Equivalent to something outside. Now I have to add further identification.
Right.
Right?
That's what I
Yeah. So when I do this further identification, now I am not looking into this interior region. I am just throwing away that interior. I keep only the exterior region,
Okay, got
so that the identification, at least the picture looks better. So if I now I do further identification, minus 1 is identified with 1.
Good.
Then what I could get is a domain which will be mapped to thrice punctured sphere in the following way. So see this
Sorry,
this
sorry, okay, I didn't understand how you got that table. I understood that you got these bands.
yeah,
But what happens in the middle?
which one here, right? So then I did further identification. I could do a shift, right? So this whole thing will be shifted to here
Okay.
with c going to
If you draw a unit circle in the data diagram,
This
is actually given by fixed points, right?
plus 2 goes to another,
Another circle outside the circle.
yeah.
So that also he takes up.
That is because the original.
But those bands already account for that.
Yeah, so this one, right?
Yeah. That band accounts 9 for this shape.
That is true.
Then why did we get the whole inner circle?
See, I have this further identification, right? C going to minus 1 by c. So I could start from the upper half plane and then do the c going to a c plus 2 identification, right? 0 is identified to 2.
Okay.
Then I could implement further identification, c going to minus 1 by c or 1 by 2c, depending on what is the, actually that's the only thing that is
Even roughly, how does that give you this shape?
Yeah, so you start from this picture where you have c identified with c plus 2, which
Fine.
give you a
Now
proper
you have
band.
A strip of
You have a strip, and then inside the strip, if I do this mapping, I will get further identification.
and it's a bit complicated to see how
Yeah,
quickly that shape.
yeah, so you have to just work it out properly.
Can't you do it the other way around?
If I do this way,
minus 1, then you get everything outside the circle.
exactly, this
Now
one,
you make further identification in the region outside the circle.
yeah,
So this circle would have gone to another circle
Yeah,
outside.
yeah.
But that's identified with the original circle, so you take that.
Exactly.
That's how.
that's the way we get it. So,
So at the point in
Go
what
ahead.
you have drawn, I mean, only 2 elements of gamma, right? I mean,
Yeah.
that's-
we have, it's generated by 2 elements. This gamma is generated by these 2 elements. Exactly, if I do further identification, I get identification like 2c by c by 2c plus 1, so you have further identification. Combined, this is a combined identification. So, exactly.
Okay, so this is not the fundamental domain, finally.
So this itself is a fundamental domain. So this itself is not the fundamental domain. See? So you have further identification such as c going to minus c by 2c plus 1. So that will provide me, at the end I will get this kind of a picture.
Something always taken off from the big unit circle.
Exactly. See, that's true. And
What is the final
yeah, so
region is the fundamental?
so this is the fundamental region. So it goes to infinity. And then I do this identification for the fundamental domain. Right? So identification will identify only the boundaries of the fundamental domain. So it's because of this further identification. C going to, it's not just,
Now that also is more.
I had the same question with you. Yeah. You've added, suppose I did something nice.
yeah,
Give it the exterior of the unit circle.
yeah.
Now you told us that the actual fundamental domain is greater than
More than that, yeah.
the
That's,
naive thing. How can that be possible? Let's draw the naive thing.
The nice thing is that strip with a unit circle removed.
Yeah. And you
so I mean, the only thing is I am a bit confused with the gamma 2 group itself. I remember the fundamental domain. If I work out the precise gamma 2 group, yeah, maybe the numbers are wrong.
might be one.
Yeah, so that's the only thing I'm a bit confused. So it might be that C going to C plus. I don't remember that precisely. But still, this is something which one can easily work out from the definition of gamma 2, and which is a subgroup of SL2C, PSL2C, and then work out the fundamental domain, which is an elementary exercise. So at the end, we get a fundamental domain of this kind.
Okay.
Now you have to identify the boundaries of the fundamental domain using this translational symmetry and this special conformal transformation. So what that does is that identify this boundary with of the fundamental domain with this boundary, and then this place will be identified, and then here again you have an identification. See, you start getting a thrice punctured sphere, right? So you are just close.
That this is not to be identified with that structure. This is the modulus space.
Which one? No, it's not the moduli space. It's not. It's actually a domain wrote on the upper half plane. I'm not talking about torus. Yeah. This is? No, it's a thrice punctured sphere. Now I'm not talking about torus moduli space. I'm just talking about the Riemann surface itself.
There are points here which are really similar actually. In this coming.
So that's why I had to do further identification right here.
Yeah. Just show us on this diagram the location of the three functions.
Yeah, so 0 corresponds to a particular function, one of them. These two corresponds to, say, infinity, and the infinity itself corresponds to 1.
Just on the diagram, where are the three functions? 0?
So 0, minus 1, 1, and you have an infinity, right? So this strip will go to infinity. Huh?
Sorry, I think 0 is outside the domain, no? I think the fundamental domain, if I remember, is that you have to take the whole circle,
Yeah,
right? And two vertical lines going up.
yeah,
So a circle going from -1 to 1,
yeah.
and two vertical lines going up.
So you
And in that picture, it looks like there are three casts, right? One at I infinity.
yeah.
Right? And then there are these two casts which are on the two.
You see, the point is that you could write down the fundamental domain in different ways, depending on what representation of gamma 2 that you use. You could have different pictures. So I could start from here and then find a mapping to the domain that you are mentioning.
And could you draw, just so that we're clear, can you draw Ashok's domain if you don't mind?
So I think what Ashok is saying is this kind of a domain, right? Is it?
Yeah.
Big unit circle,
Yeah.
the thing.
Exactly. This is maybe this is the thing which I wrote with this group, right?
From the edges.
Exactly.
And
So
those lines hit at what point?
it should be. So when is it? It's hit at minus half, right? So you have C going to C plus 1, right?
Yeah, I take no, 0 to Z plus 2. So from -1 to +1, you draw two vertical lines.
Okay.
Right?
Yeah. And here, right? This is the picture that you have.
And yeah, and I think then it's folded somehow, right?
Yeah, it's folding, right?
So, but that curves to plus.
Then at 0 you have a curve point.
Yeah. At I infinity there is some certainly cast point.
So there is a cusp point, right?
Yeah. Yeah.
So actually you are missing one puncture, right?
Yeah.
So that's a. So you are supposed to identify these two sides, right? So the -1 line and the 1 line, right?
Yeah.
Okay.
Then you get a cusp at infinity, that's for sure. But you are missing. So
Really, can you write down your transformation dots?
C going to C plus 2 and C going to -1 by C.
This is, you think this is gamma 2?
So that's why I'm that's why I'm slightly confused. I don't remember the I don't remember the precise form.
So not 2 Z.
Yeah, I think gamma 2, I mean, if I remember, is A, B, C, D.
Yeah,
With the condition that A and B are 0 mod 2.
yeah,
Sorry, A and B is.
precisely.
B and C are 0 mod 2,
Yeah.
and A and D are 1 mod.
Exactly.
Right?
Yeah.
So 1 by Z, -1 by Z is not allowed.
Yeah, I think 0 to -1 mod Z is not part of gamma 2.
Might be as -1 by 2C. or definitely it's minus c by 2c plus 1. Maybe that's the thing that you,
Yeah.
right? So is c going to c plus 2 and minus c by 2c
Yeah.
plus 1? Yeah, I think, yeah.
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 Yeah, I think that's,
But you could combine these two transformations to get a different representation of gamma 2.
yeah.
So this is one choice of basis, or I could choose another. Maybe I took the wrong basis.
Okay.
Yeah. So with this,
Mainly the class will be at I infinity and its images somehow, right?
that is true.
But by its images under SL, by under images under SL2C, which is not under gamma 2.
Exactly. That's true.
Yeah. Okay.
So at the end, if I work out the fundamental domain properly, you could get a picture of this kind, where you have cusp at -1. I mean, in the fundamental domain, I have cusp at a point which lands on the real line at -1, 0, 1, and I have the strip is going to I infinity. I infinity will be mapped to 0 of the sphere, and then 0 will map to 1, and -1 and 1 will map to infinity. So this is one example of Fuchsian uniformization that you can get.
And so near the singularities, there will be a singularity of the. How do you see that this is a singularity?
So if I, you mean, so the point is that first of all this point is landing on the real line.
What?
On the real line, which is the bound.
If I write down the metric in the neighborhood of that singularity, what will I see?
Oh, you will see the, you will see a logarithmic singularity.
I see it. Oh, so it's not just at a point. I can't even transform it away in a neighborhood.
In the neighborhood, you can find a transformation. Say for the I infinity case, I can write down simple transformation. So the identification is c going to c plus 2, right? So a transformation that, so you are looking for a coordinate near the infinity, right? Which is like e raised to minus pi I c. Right, so w, and then you have to express w, I mean the metric dc by imaginary part of c whole square in terms of this local coordinate w, which already includes the identification that you are supposed to do at the infinity.
Yeah, so what I'm trying to understand is the identification of an Oberfold, is the singularity of an Oberfold surface.
Yeah.
That you cannot see infinitesimally away from the point.
Yeah.
It's not a curvature kind of thing.
So even at the infinity, even near the boundary, or even near the the puncture, you won't see any singularity for this metric, right? This is a metric which has same curvature everywhere.
Exactly.
So that's why the picture is not like a puncture. So the picture of the surface is like something going to infinity, a cylinder going to infinity.
Yeah, but Rohit, actually it's not in the hyperbolic metric, it doesn't look like a cylinder, right? Because it's like dc
Yeah.
over mod d squared log d squared or something.
Yeah, it's like a hyperbolic cylinder.
Yeah, like a hyperbolic cylinder. So it's not, so integrated curve, the curvature is actually infinite, right?
Yeah.
Because
So that's why locally everywhere it has -1 singularity, right? So
Exactly.
so the region is has infinite size. So if I integrate, I will get infinity.
it'll get it.
Yeah.
But could I pull this into a finite point?
So you will.
What I'm trying to understand is the curvature singularity localized at that point, or can you see it in a neighborhood?
No, here actually you are distributing
Or
this.
it's not a perfect way?
Yeah. So this metric distribute the singularity all over everywhere, right?
But if I pull it to a finite point,
Yeah. So then you have to use some other picture, which is like Sibel differential picture.
suppose I do that. I bring that point to a finite point.
Yeah.
Then will I see curvature diverge as I approach this point?
Yeah. Yeah.
So it's like the singularity of a normal black hole, not a BPZ singularity, right?
Yeah. Yeah. So you can localize the curvature to somewhere
So
to
the
this.
curvature goes to infinity in the limit. It's not just infinity at that point.
At that. Oh, okay. Yeah.
Is this right?
Yeah. That's
I'm
true.
asking.
Yeah. Yeah. So it's like the I mean you. Here, right? So you have this identification, right? Here. Yeah. So he. Yeah. Yeah. So it depends on what kind of. So at least in this picture, like Ashok was saying, the integrated curvature will be infinite around that neighborhood, or that's why it's a cusp. But if I look into local curvature, which is like Gaussian curvature, it's constant all over the surface. Doesn't matter where you are looking, very near to the puncture or away from the puncture. So to compensate for that, like when you go for near to the puncture, In the complex plane language, I mean the metric diverges exactly there, but the hyperbolic metric, what it does is it makes the size of the tube very long, so that only the integrated curvature will be infinite, the local curvature will be a constant object. So this
Since Siraj's question, is that dg mod square or mod d square log mod d square?
yeah.
That's the kind of parameter.
Exactly. So if I write the hyperbolic metric near the cusp using the local coordinate there. So I have so W is the local coordinate near the puncture. So then the metric looks like mod of dW whole square, mod of W whole square, ln mod of W whole square. This is the kind of metric that you have. So it depends. Yeah, you can. Exactly. So what you can do is you can start from the Poincare metric and substitute the C with the local coordinate. So the relation is that W equal to e raised to 2 pi I C. So if I substitute that, then or replace Poincare metric with this local coordinate, I get this expression. Now the point is that the near every cusp region for any puncture on the hyperbolic metric, if I use local coordinate around the metric has the same form. It doesn't matter whether the location of the puncture is at infinity, 1, 0 or any some random point. Everywhere near the puncture you have same form of the local metric, which is this.
And in this form of the metric, 0 is infinitely far.
Exactly. That's why you have this infinite long cylinders.
Okay.
If you were to do this for Venus too,
Yeah.
then you won't get discussed, right?
We won't get discussed.
How does this look like? This
So-
motion we have. How does the region look like
So the region looks like
after that?
so you have several hyperbolic hexagons.
So nothing goes to the 0.
Yeah, so the point is that you will get a puncture only if the fundamental domain lands on the real axis or at the infinity.
Right.
So this picture, it's like you start from a genus 2 and then cut along several different non-trivial cycles. So in Fuchsian group language, a geodesic that has a finite length in hyperbolic measured in hyperbolic metric corresponds to an element in Fuchsian group which we call as hyperbolic element of Fuchsian group. And an element in gamma or Fuchsian group that corresponds to a puncture on the surface are called parabolic elements. So the criteria for distinguishing parabolic and hyperbolic metric is hyperbolic element is the following. If you take an element of Fuchsian group, you can see that a hyperbolic element has 2 fixed points. And if you compute the fixed point of a parabolic element, that's actually 1. So you can think of it's like you start from a hyperbolic element, then take the fixed points to a same location. So it's more like starting from a geodesic that has a finite length and reducing the length of the geodesic to 0. So going from hyperbolic element to parabolic element in Fuchsian language corresponds to taking sort of a degeneration limit.
So does that double pole become like, does the W square become like W minus A into W minus B or something?
So here, so you are saying near the
Yeah.
boundary.
It's limit you're talking about.
Yeah. So if I start from a border which has length which is not equal to 0, then the local coordinate is slightly different, and you get a metric that looks slightly different.
So that doesn't have only, instead of quadratic singularities in the denominator, does it have only linear
So
singularities?
it's more like a sine hyperbolic function.
That's fine, but near the zeros of the sine hyperbolic function, is it a linear singularity?
You can, if that means you are you taking this limit length goes to 0, right? So you will come to this kind of a metric.
In other words, saying is that in those cases, the geodesic length to that point is always fine.
Always find it, exactly. So this is the basic.
If the embedding of that group, then it changes.
Exactly. So if I change the embedding, so that's more like the story of mapping class group transformation. So the basic idea is that you can start from upper half plane and find appropriate subgroup of the isometric group PSL2R and then do a modding to get the Riemann surface of your interest.
And if you have a sphere with n punctures, it's some very complicated kind of identification. You need n cusp.
Yeah, you need n cusp. But the story is exactly same. It's not much complicated. You have to just merge different fundamental domains. So the basic idea which make hyperbolic geometry.
Four punctures, the one that we're familiar with Virasoro Shapiro, is that something like?
I mean, you
Because
final
you can
answer.
only do integrals over again one loop. You have to get.
You can do that, but the story is slightly more difficult. I mean, there is a lot of details for doing it, because there you have to worry about all this mapping class group transformation, which requires recent developments if you want to get a handle.
That development you want to do integral over modulus space. Modulus space will,
Yeah.
in this example, it was just point.
Yeah, in this example it's just a point, because it's a gamma 2 group, right? There is no further parameter.
So you will show us.
I won't show any explicit calculation. So the basic idea of this talk is, our lecture series is to discuss the basic geometry of string theory, how to construct everything in principle. Now you can, I will spell out all the rules that one requires for doing an explicit calculation in string perturbation theory, or computing the action or finding the action.
How to understand the modulus space and
That I will describe. So that you mean the parameterization of, so that I will describe. So then, now I told you that every single element that belongs to a covering group corresponds to a non-trivial cycle on the Riemann surface, right? For the Fuchsian group, every single element which can be thought of as a 2 by 2 matrix. Then if I compute so this gamma corresponds to a particular geodesic on the Riemann surface, C gamma. Now from the gamma you can understand what is or you can extract what is the length of this geodesic. So you have a geodesic on the Riemann surface, C gamma, corresponding to this C, I have an element in the Fuchsian group, which I can write as ABCD. Then
I didn't understand. You chose this geodesic in some special way, or it's an arbitrary?
I'm just saying that there exists a geodesic, and corresponding to this geodesic there will
Is this a special geodesic or a geodesic?
any simple it's a special geodesic in the sense that they won't intersect to itself. It's a simple closed geodesic. It's just a general simple closed geodesic
Simple close meaning it comes back to itself.
itself, right? So
In
it
smoothly.
it could go this way also, right? All these non-trivial things are fine.
But it comes back in an angular way,
It-
not at an angle.
Yeah, it will smoothly join. It's a smooth curve on the geodesic on the Riemann.
It's a generic geodesic of this form?
It's a generic geodesic of this form.
No, sorry. Is a generic geodesic in this metric of this form?
Yeah. Yes. Yes.
Okay.
So
Yeah, you
Sure.
might imagine that it comes back quick. It's not funny.
so if
You know, that's what you have to do.
because if you take all the space of curves, you know,
exactly, yeah,
That's
they are smooth. So these are minimum length curves, right? So that's why I call it geodesic.
So Rohit, again,
Huh?
so can I ask something? So these are minimal length in a given topological class, is that
Yes.
what is considered?
Yeah.
So it's okay. So not arbitrary geodesic in that topological class, but a minimum length
Minimum length one.
geodesic in that.
Exactly. So that
Okay.
geodesic has a particular representative in the Fuchsian group. By that I mean a particular element in the Fuchsian group corresponds to a specific geodesic on the Riemann surface. Huh? Oh, so I mean that any gamma on the action of gamma on the upper half plane has something. I mean it takes you through a geodesic on the upper half plane, and then you are doing some identification. It's a bit more, a little more detail is there. Like you can work it out.
No, but you don't understand.
Roughly, the point is that see, you have this fundamental domain, right? For the sphere with 3 punctures. Now I want to understand there is no further geodesic on it. Still, I just want to give an idea what is.
See, I think we understand that given a topological class,
Yeah.
there is a minimum length geodesic.
Yeah. Yeah.
So you're going to tell us how you're going to associate an element of gamma with a topological class.
Exactly.
I don't understand that. actually.
So let's consider a situation where you have a simple closed geodesic. So you can consider a situation where you have 4 holes on the sphere, and then the fundamental domain looks like here you have a particular hyperbolic hexagon, which I won't really draw. That's not necessary. It's a hyperbolic hexagon, and here also I have a hyperbolic hexagon. So I have to join this hexagon along the imaginary axis of upper half plane, and then implement further identification if I require. So that's what I'm supposed to do. So then this geodesic, a geodesic along this cycle, can be understood as a straight line that connects these 2 points. Now assume that this point and this point is identified. Right. So it's
easier to understand it in hyperbolic plane.
exactly. So this is hyperbolic plane, right? C going to lambda C.
But we
This
understand that all geodesics in the hyperbolic plane are generated by
elements of SL, PSL2R.
They are boosts or rotation.
Exactly.
Geodesics are either
Closed circles
or
or a straight line going to infinity, right?
So when we model by this, there are certain geodesics
That will get identified, right? So these are the geodesics on the upper half plane will get identified under this identification using Fuchsian group. So those geodesics that are identified under this identification will become a geodesic on the Riemann surface.
So I didn't get that. So that's the upper half plane. You've got various geodesics. Like, I mean, yeah.
Perhaps it's easier to see it in another coordinate system where
So
it's
you have,
R2,
yeah, you,
where it's SO2, 1.
so if you look into the Poincare disk, so the fundamental domain looks like this.
Associated to a point.
Associated.
To an element.
So see, the point is that each element does a particular identification, right?
Yeah.
So that identification will identify a specific geodesic. So see, these boundaries are identified. Then you have a geodesic that connects these 2 points, which has minimum length on the upper half plane. So under this particular identification, these 2 points will get identified, right? And then that becomes
This is kind of the same thing why gamma was the fundamental.
exactly.
So that's the topological class and gamma.
Depending
Yeah.
on different gamma, you will get from the same geodesic on this hyperbolic plane, you will get more than one geodesic on this plane.
No, no, no. No, for a single element in Fuchsian group, that corresponds to a single geodesic.
For a single geodesic on this on this plane,
Yeah.
if you take different gammas, then you will get different geodesics on this plane.
So that corresponds to different ways of identifying things, right? I mean, which one is, I mean, so here I am identifying a particular geodesic, right, with a particular identification, and that identification will provide me a specific geodesic on the surface.
Specific thing is because it fits a particular gamma.
Yeah, so if I choose another gamma, this geodesic will not get identified. Some another geodesic on the upper half plane.
That will again be a geodesic.
That will again be a geodesic, which becomes another geodesic on the Riemann surface. So each geodesic will be associated to a single element in the Fuchsian group.
Fuchsian
Gamma, yeah.
Joji, so can I ask this following question? So what you are saying is that for every non-trivial topological cycle, there is a gamma. And
Yeah,
that
that's-
is 1 to 1.
That's true, yeah.
That for a single gamma, there is a non-trivial topological cycle and vice versa. Right?
Yeah, yeah. That is true.
And then the minimal length geodesic in that topological class is what you are identifying.
Exactly, exactly. That's true. And then I'm measuring the length of that minimal length geodesic.
Okay.
So if I denote that particular minimal length geodesic by C gamma, then the length I call it L gamma. So what I am claiming is that the length of this minimal length geodesic C gamma can be expressed in terms of the parameters of the element in the Fuchsian group. So let's say I have Fuchsian element gamma, which is A, B, C, D, a 2 by 2 matrix. 2 by 2 matrix. Then what I am supposed to do is I am just supposed to take a square of the trace of gamma, which is just A plus D all square, and that corresponds to 4 into cos hyperbolic L gamma by 2 whole square. So this is the relation. This is something which one can prove with using elementary trigonometry. So I am supposed to just the trace of a element in Fuchsian group is related to the length of the geodesic. Not directly length, is a cos hyperbolic of the length. So from here what you can see is that if I take L gamma to 0, I am making that geodesic to shrink to a point, right? So it's more like looking into degeneration. Then, or you could think of a boundary having length L gamma will is shrink to a point. In that situation, this relation says that for this cos h, L gamma will become 1, and then trace of that particular gamma or trace of gamma whole square become 4. If an element in the Fuchsian group has a trace whole square equal to 4, then that element is the parabolic element. So that's why I'm saying a parabolic element can be mapped to a puncture on the Riemann surface, and a hyperbolic element can be mapped to a simple closed geodesic on the Riemann surface.
Yeah, and this is basically the point that you can go as near the puncture as you want.
Exactly, that's true.
That's
Yeah.
why I did it.
Yeah.
So in this case, either B or C should be zero.
Either B or
B
C.
or C should be zero.
Yeah, depending on I have to preserve this relation. AD minus BC should be equal to 1.
Yeah.
Yeah.
And AD is, so you are saying A plus D is 1.
A plus D equal to 2, plus or minus 2,
2, yeah.
plus or minus 2.
Okay.
Then
So that implies B or C should be 1 or 0 or not?
I could have situation where I have 1, 1, 2, right? See, let me see.
But that should be
Zero,
two
yeah.
should be zero.
Minus 1, 1, 2.
Okay.
So 1, 1, minus 2 or something, whatever, right? AD. One. Yeah, so if B is 0, C could be anything. Sorry, if B is 0, C could be anything, right? This is a parabolic element,
Yeah.
right? Which preserve all these conditions.
So like, okay.
So a puncture looks like 1, 0, C1, right?
Okay.
Yes.
Yeah.
Or different representation, right? So that corresponds to this. Yeah, whether it depends on whether, if you are choosing, say in our gamma 2 representation case, if I choose this to be equal to 2, then this is doing this transformation, C going to C by 2C plus 1. And if I, instead of making B equal to 0, I can make C equal to 0, and then put B equal to 2 or something else. So that corresponds to a translation, C going to C plus 2. Right? This corresponds to puncture at infinity. So this is the way punctures or simple closed geodesics are related to some elements in the Fuchsian group. So the basic idea is that you can start from upper half plane, identify the upper half plane under some subgroup of the isometry of Poincare metric, and obtain a Riemann surface. And there exists a map, at least locally one-to-one map to the region inside the moduli space.
So this measure that you wanted to look for becomes a group theory question. Is that the point?
Yeah, it's more like a group theory question. And the nice thing is that you see, you are able to obtain complicated Riemann surface from a simple region, right? In upper half plane, you know upper half plane, you know the full trigonometry of upper half plane. If you want to do a calculation in Riemann surface, you are supposed to do a calculation on upper half plane. Then you have to just deal with hyperbolic functions, which is much more simple. So I mean, I was kind of really excited when I started learning Polchinski. It looks like after some calculation, he goes to full Riemann surface and then talk about big objects on the Riemann surface, and I didn't have any idea how to get a control over any of these objects. How can I do a calculation on a Riemann surface? So we just say that Riemann surface is defined using complex structure, and we say you have several domains, and how will you do any calculation? So you want some, if I use this idea of universal covering, I can go map any calculation on a complicated Riemann surface to a calculation on upper half plane, which I know how to do. So that's a big advantage of using Fuchsian representation compared to any other representation.
This kind of this modular space is not quite clear.
I haven't come to that picture.
Spelling itself seems kind of somewhat complicated.
No, the point is that so your question can be thought of in the following way. Let's say I somehow found a characterization of Teichmuller space. Let's say for now just talk about Teichmuller space, and then is it possible to associate a particular point on the Teichmuller space to a particular function group, right? Is that your question? The answer is yes. It's actually a simple thing to do. For any point on before modding on. Exactly. Now to understand the details about a mapping class group, you need little more inputs. That can be obtained from upper half plane. That's another beautiful thing. That's due to the work of Makshain and Mirzakhani. So that's like a breakthrough. So here we see that a calculation on Riemann surface can be converted.
Degenerations are kind of understood like just the elements of.
Yeah, somehow a parabolic, hyperbolic element is becoming a parabolic element. So all calculations on the Riemann surface can be done on upper half plane. Now later we will see that all calculations that you are supposed to do on a moduli space can be performed on a simple n-dimensional space, whose structure we know. And at the end we are supposed to do some integrations over some real parameters, which is extremely simple. That's one motivation. Anyway, I said some statement. I will describe how to really get into that picture where we will be able to do integrations on Riemann surface on moduli space. So by that I mean, if you can calculate the string measure, you will be able to compute the amplitudes, and you can get numbers. It's not that you get some mathematical object. You can get numbers.
So one never needs to learn about Hygienus, theta functions and so on.
So, but the point is that there is a catch. We know about theta function because of the work of big mathematician. They did a lot of work for several years.
Yeah.
That's why at the end we came to know about theta functions, and still with theta function you can't do any simple integration, right? We have to do some integration of theta function.
Non-denomination theorems are
Exactly.
proved using theta function.
That is true. So you have to just utilize nice properties of theta function, and those Fay identities and all they came from before this idea of bosonization. All those things came from some work of mathematician. Then once the idea of bosonization came, you came to know a lot about theta functions, right? Still, if you want a number, like let's say you want to compute mass renormalization or mass of a particular excitation in string theory, then you are supposed to do all these integrations, right, to finally get a number. Say at some point somebody found a way to connect string theory to experiment. You want to make predictions, right? So you want, just like in quantum field theory where people develop techniques or software for doing integrations, we need some similar things, right? At least we need a precise expression which you can feed into a computer without any ambiguities about MCG and all, right? So this is something which we can gain here. Now I didn't complete that answer. So what I am saying is that so far we know our computations in string theory depends on our understanding about theta functions or our understanding about correlation functions of some simple CFTs, right? Now in this language I am going to some different parameterization. There I am using this, I am looking into specific kind of amplitudes with specific number of genus less than or genus less than 2, where I can use characterize a moduli space using the period matrix. Now theta function is a function of a holomorphic function of period matrix, right? So there we have this advantage of using the power of holomorphy. So you can use the analytic structure of theta function to learn something about, learn the structure of the amplitude. Now, but still performing integration is extremely difficult. I mean, the point is that even for genus 2, you don't know what is a fundamental domain that that corresponds to a moduli space in terms of period matrix. You don't have a clear region that specifies for this particular value of tau. You have a different value, different Riemann surfaces. So still, even for genus 2, using period matrix, you don't have a clear region that represents a moduli space, so that you won't be able to evaluate. There is an equal. So you have this Schottky problem, which says that I mean for every period matrix there is every Riemann surface has period matrix, right? But two different period matrix may represent the same Riemann surface because of this all this modular invariance, right? So which is a difficult thing to solve. Maybe one can write down powerful computer program to really determine it, but beyond genus 2, the dimensionality of period matrix becomes is more than the dimensionality of moduli space, right? still then you won't be able to do any calculations. So here what I get is I am parameter. I will show that I can parameterize the moduli space of Riemann surface or Teichmuller space of Riemann surface using some simple parameters known as Fenchel-Nielsen coordinates, this twist length coordinates, and using that I can perform. I can at least write down an expression which can be feed into a computer. Now there I have two data I need. I need this data that corresponds to construction of measure and then the correlation function on a Riemann surface. So the story is that can I compute the correlation function on a Riemann surface in terms of these parameters? Or in other words, can I find a relation between P, given a point in the moduli space represented using Fenchel-Nielsen coordinate, can I find what is the period matrix? So this is a simple technical question. If one can solve it, then what I am claiming is that I will be able to write down an expression which can be fed into a computer and do the calculation.
Sorry, I was going to ask you exactly about that. So if we just focus on, you've given us a particular metric on a Riemann surface.
Exactly.
Now, if I wanted, suppose I knew the problem of, let's say I have the free boson plane, and with this metric on that, on the upper half plane, I compute all correlation functions.
Yeah.
Now, from that, can I go to the answer for your correlation function of interest? From that, knowing gamma, can I get the correlation function that you actually want?
So can you repeat? You are writing a bosonic theory on the hyperbolic Riemann free bosons
on your upper half plane.
Yeah.
And it should be reasonably easy to compute all correlation functions
Yeah.
of arbitrary insertion, the vertex operators.
Yeah.
Let's say exactly on vertex operators.
Exactly.
On this upper half. On this upper half. Okay. Now, you might think that what you want to do is to take that answer and mod out by gamma.
Exactly. You can use this idea that we use in electrodynamics, taking these images.
However,
right?
the places where you're putting your operators are rather singular points.
That's true.
And I was wondering whether that's going to cost.
So it's more or less asking the question that you want to compute a green function on a Riemann surface which has singularities at the punctures, right?
Yeah, I mean the upper half plane was nice and smooth. I compute all green functions there.
Yeah.
Then you do some identifications that have some singularities.
Yeah.
And you want to put your insertions at those singularities.
Yes.
And I was wondering whether that's going to cost. Looks like a singular place to put the items, but you're forced to do it.
Yeah, we are forced to do that.
So
I mean, this
it's possible.
I think it should be possible, but I haven't done any calculation so far.
Just for 3 points, for the sphere with 3 points.
Yeah, one can for sphere with 3 points. The good thing is that we can do it with your way, or you can find.
You can do it many other ways, but can I do it my way? Because this
you
is
can do it definitely. I think you should be able to do it.
Okay, thank you.
I think there is nothing which is preventing.
Sorry, can I ask something? To define an optical amplitude, I think what you want is not the hyperbolic metric, but the metric which is non-singular at a function, right?
Yeah.
So you have to make a transformation. That should be easy to find, but it is not that what you want is the correlation function with the hyperbolic metric.
Yeah. So the point is that that's true. So what you can do is you can do a transformation, right? If you can find a conformal map from complex plane to this one, we can always transform the answers.
Yeah, locally. You have to do it only locally.
Yeah, we want to do it locally. That's true. So you can think of you are inserting your vertex operator on the actual surface, and then I can think of transforming it into hyperbolic metric.
Hyperbolic.
Yeah.
So two singularities will cancel.
Exactly. That is true. And then the singularity coming from that will cancel. Right.
Yeah.
So this map itself is not a nice map. It actually has a map with singularity.
Yeah.
That is true. So you should compensate for that.
So this potential procedure, essentially I needed to construct Venus, right? Not
Even for punctures you want. Even for punctures. Even for punctures you need identification. Right. You have a flat plane, right? You start getting non-trivial geodesics. How? By doing identification. Even for a thrice punctured sphere, you have to do identification.
Right puncture sphere, I could just put the vertex operator on the sphere and compute the total.
That is true. So, but what Shiraz was asking in terms of hyperbolic plane, can I do a calculation in hyperbolic plane and transform it into a calculation on the complex on the thrice puncture or four puncture sphere? By doing this idea that you have these images, just sum over all the images to make the function symmetric, that respect that then make that function to be a function on the sphere.
Like doing it twice, right? So you already have vertex operator, but you already have singularity. So I didn't quite understand what you were saying.
But the singularities are in the description of the moduli space of insertion. But you also need the integrand.
Integrand, yeah.
That's just some correlation function in conformal field theory. That you have to compute somehow.
Yeah,
So in this picture, there's only one place where to insert that thing.
that's true.
So it's like you're computing a conformal field theory correlation function at a singular point on the manifold. But like Ashok was saying, you probably have to have a singular. So you have to
Yeah.
be able to regulate the singular. That sounds like the important.
Yeah, that's true. Yeah, that's true.
That makes it immediately much more complicated than doing method of images because.
So what you can do is you can make it any punctured sphere into a sphere with holes, and make the metric bit better
You need to know grid functions in that.
in that
kind of
picture.
this.
Exactly. I don't see any reason.
Even though it's complicated, it looks like that you have to do it once because I mean all functions locally have exactly the same geometry.
Exactly, it's the same geometry.
And you have the same transformation every time. Right?
Exactly, that's
so
true.
once you know how to do it once, you can do it in all cases.
That's true. Yeah.
Yeah. But you have to be very careful that your method of regulation is the correct one. That doesn't infringe.
Exactly. Yeah, I agree. And that may be what you are saying. If you can make it into a hole,
Yeah. Instead of a puncture.
Puncture, you make it in a hole and put some wave function, right?
Yeah, that's true. So that's the picture I would like to. I mean, I prefer. Like that looks more nice. I mean, it looks like okay, you have a string coming. It's precisely like looking into target space. How I mean, strings are moving and then they collide. So it's more nice in that way. You are actually seeing strings, right? Then if you want to map it to complex plane, you can do it. So that's like solving this problem of inverse uniformization. So going from upper half plane to complex plane. This is something one can, in principle, one should be able to do. But I mean, this is a question which I don't think mathematicians understand properly. They don't have a clear answer. How to really map a
And since you have a canonical metric,
yeah.
I can imagine that you can regulate it simply by reminding that the length of the geodesic
Yeah.
is some epsilon, right?
That is
and
true.
you use the same epsilon for all.
Exactly.
Right?
That's true.
That
Yeah.
should be natural regulation.
That's true. So that should be a natural
The
regularization.
length of the surrounding geodesic.
Yeah, length of the surrounding geodesic. Because like a canonical metric.
Your
That's universal.
surrounding G.
I mean, the length of it going to 0.
Yeah. So that's true.
So, sorry, instead of constructing models for complex space, if I were to put, let's say, a bunch of operators on the upper half plane and with all their images
Yeah.
modeled out by some gamma scalars and higher objects,
Yeah.
would that not give me?
You should give like so. It should.
Give you a correlation, but the danger is that now your gamma has been chosen such that one of your operators is at a singular
It's a
point.
singular point. Yeah.
No, but there is no singular point. It's just a genus 2 type of model.
Yeah. Then you don't have any
You're
extent.
dividing up the moduli space into moduli space of Riemann surfaces and the puncture.
Yeah. So that actually the point is that the idea what Abhijit is saying, I mean, it's actually a nice thing. So you could always think of a punctured sphere, or you can make the punctured sphere to a sphere with holes, and then you can identify some of the holes to get higher genus where you don't have any external states, and then what you can do is after doing the calculation, the gluing should be done in a way that people call, this doubling trick that you use in CFD. So you have a manifold with boundary. When you do this, so you start with open string, and then using this doubling trick, you can make it into a closed string, right? So similar thing can be done for a sphere with holes, and then make it into a higher genus surface, and then demand that that higher genus surface has a particular symmetry. With that symmetry, you can do the calculation, and at the end, you can just make the geodesic length goes to 0.
And so just let me understand this. Mathematically, is this splitting into, is this like moduli space a direct product of two things? Is that a precise statement?
Yeah. So I mean, if
Or
I
is there some obstruction to doing what you
I mean, this is something which you can do. That you can split the moduli space into two halves. You can start from a higher genus to a higher genus surface, and then find a subspace in the higher genus surface, which corresponds to actually surface with borders.
But globally, you can always do this. This is the kind of thing that mathematicians love telling you there are obstructions.
Yeah. So
Conventional theory does not guarantee this, right? The thing that Shiraz is worried about.
no, what Shiraz is worried about. This is the way actually people do calculation. Mathematicians do a calculation
Why
for.
don't you do that? I
Yeah, so that
generate those.
exactly that's what we are supposed to do.
No, but
When,
these are-
what I'm saying is that Abhijit's idea of computing things on higher genus surface without any punctures. This is something which one can do.
No, this one can do, but I thought what you have is a nice representation of the whole moduli space of total thing.
Total thing.
Now, Abhijit's idea will require you to split up that moduli space into a product of two things.
That is true. So I'm saying that I don't want to do. I mean,
And
for
that way you
doing
have this nice structure.
exactly, I don't want to do calculation on moduli space using that idea. But if I want to compute some object on Riemann surface itself, I can double the Riemann surface, make the punctures disappear, and then I can get a compact closed surface. Then at the end, after doing the calculation, it's more like looking into factorization. You can start from genus 2 calculation, do the factorization, get the 4-point function. I mean, if I want to stick, if I want to forget about punctures, if I want to forget
No, the
about,
logic
but
of-
that's not necessary.
The logic of the first part of your procedure requires you to put the
Insertion at singular points, right?
And
So that's true. That's true.
okay.
That is precise.
The problem seems to be, I mean, not so much that it's a, I mean, it is a semi-direct product, that you can first define the moduli space and then put the punctures on the Riemann surface, right? But what you lose by that is the degenerations are not, I mean, properly described.
Yeah. So in this picture,
The fact that if it is a higher genus surface and degenerate,
yeah,
it becomes a product of two punctured Riemann surfaces and this additional gain parameter.
yeah,
That is more obscure in the other way of describing, right?
Yeah.
You treat the puncture separately from the
that's true.
rest of it.
So in this the uniformization that I do here, I can't really distinguish what part of the moduli parameter corresponds to a puncture and what corresponds to a genus. So the moduli,
Degenerations are in some sense easier to describe, right?
yeah, yeah,
In this language.
yeah. So whatever is the thing, at any rate, I am assuming that if one can compute correlation functions on this upper half plane and then get correlation functions on the Riemann surface, this is something which one has to do, because anyway that one has to do that depending on which string theory that you are dealing with, right? So if you are interested in some particular string theory defined using a particular target space, you have a specific conformal field theory. You have to compute the correlation function in conformal field theory. So that's a one thing that one has to do. And I am mostly interested in the remaining geometry of the amplitude. Assume that I have a particular target space, that means a particular CFT, then how will I construct amplitude, or how will I construct a form on the moduli space? Exactly, that's true.
So you can think of the group of lines which is at the subgroup.
Yeah,
Same with these lines which circle around the function.
around the
Then
function.
you can think of this as a subgroup of the group. So that's the way more or less to handle this.
Exactly, yeah, yeah. So I think already one. Yeah. Okay, then I can stop it.
Yeah.